Today we're going to look at problems which are referred to as optimization problems. So let's start with this one. We have a rectangular pan. It's made by cutting out squares from the corners of a 25 centimeter by 40 centimeter rectangle. You've got that picture in the center of tin. And then we're going to fold, after we cut those out, we're going to fold up the sides to make a box. What size squares should we cut out to produce this cake dish of maximum volume? So the first thing we need to do is label our picture. And so it's a 25 centimeter by 40. So let me call the squares that I cut out, those will all be x by x. So then what does that leave? For the shorter side, we'll have 25 minus 2x. And for the longer side, we'll have 40 minus 2x. So in our picture after it's folded up, the dimensions are 25 minus 2x by 40 minus 2x by x units, x centimeters tall. Okay, so we've taken care of that. Now, what size squares must be cut out to produce maximum volume? So we're trying to maximize the volume. So what's the volume of this shape? Well, it's length times width times height. So x times 25 minus 2x times 40 minus 2x. So we have a function here, and it's going to be a polynomial. And to find out when it has a maximum, we need to find the derivative, set it equal to 0, and then verify that indeed it's a maximum. So that's the goal. So here we go. We're going to write a function in terms of x. And if I multiply that out, let's see, I'm going to have 25 times 40 is 1,000, so we're going to have 1,000x. And then we're going to have negative 80 and negative 50, so negative 130x squared. And then plus 4x cubed. So now we want to find the derivative of volume with respect to x. I'll switch the order here, so we're going to have 12x squared minus 260x plus 1,000. So we want to set this derivative equal to 0. I could factor out a 4, and that leaves me with 3x squared minus 65x plus 250. And then I can factor that, hopefully. 3x squared, so it's got to be a 3x times a 1x. 250, so they're both going to be negative, as we add up to negative 65. What if I did 5 here and a 50 here? That's going to give me a negative 50x, and a negative 15 is negative 65. Of course, if you have a calculator, it might make it a little easier for you. So that leaves us with either 3x minus 50 equals 0, which would mean x is equal to 50 over 3, or x minus 5 equals 0, so x is equal to 5. Now, something that usually I do at the beginning, but I wanted to show the reason why it's important. Look at the picture. Is it possible that x could be 50 divided by 3? 50 divided by 3 is what, 16 and 2/3? So if x was 16 and 2/3, that means that this piece here is 16 and 2/3, another 16, that's already 32. The entire side is only 25. So it's important to look at the domain of your function when you're applying it. So the domain of this function is x has to be greater than 0, but then it's going to have to be less than 12.5, because 2 of these x's here have to be less than 25. So x has to be less than 12.5. So because of that domain, I can throw out 50 over 3. So the only possibility I have is x equals 5. Now, what's left is to verify it's a maximum. So 2 ways we can do this. We can make a sign chart. Now I know x has to be greater than 0 and less than 12.5. So, and we got x equals 5. So here's my x values, and here's my v prime values. and the derivative is 0 when x is 5. So let's pick a number smaller than 5, like 4. Let's get an arrow. So here's my derivative. I'm going to use the factored form. Well, that's positive. If I plug in a 4 here, I'm going to get 12 minus, that's a negative value, and that's another negative value. So negative times a negative would give me a positive. And then if I pick a number bigger than 5, like 6, and I plug it in, that's going to be a negative value. That'll be a positive. A negative times a positive is a negative. So this tells me that if v prime is positive, then 0, then negative, that v is going to be increasing, levels off, and then decreasing. So I have a local maximum at x equals 5. Another way I could have done this is, instead of using the sign chart, I could have actually calculated the second derivative. And that's easy for this one because it's a polynomial. So the second derivative would be 24x minus 260. And if I evaluate that at x equals 5, I'm going to get 520. I'm going to get a negative value. So v double prime is less than 0, which means that v is concave down at x equals 5. And since the first derivative is 0, we know we have a local maximum. So two ways to do it, sign chart or second derivative. Depending on the function, sometimes it's easier just to do the second derivative, like in this case. All right, so now we go back up. What size squares must be cut out? So let's make sure we answer our question. So 5, our units were centimeters, by 5 centimeters should be the size of the squares that are cut out to maximize the volume. Sometimes the question will say, what is the maximum volume? So then we have to evaluate v of 5, etc. So always go back and reread the question. In the notes, I'm going to skip the next example. Let's go to this example. A 4-liter container must have a square base and vertical sides. So step 1, let's draw this picture. And see how well I can do this. Okay. Here we go. And let's label it. So it has to have a square base. So let's call this x by x. And then we don't know how tall it is, so we're going to have to use another variable. Let's call that h. Find the most economical shape in terms of material needed. So now we're not talking about maximizing the volume. We want to minimize how much material we're going to use to make this. So we need to look at the surface area and find the minimum surface area. So that's the next step, is deciding what is your function that you're trying to maximize or minimize. So we want a surface area. I'll just call it A. Maybe I'll call it S. So surface area. What's the surface area of this shape? The bottom is x times x, or x squared. And then each of the sides is going to be x times h. And there's 4 sides. And it's an open top, so we don't have an x squared at the top. So that should be our surface area. Now notice, we need to write this, I'll just call it area, we need to write this in terms of one variable so we can find the derivative, because we don't know how to find the derivative of functions of more than one variable, at least not yet. So I think I want to write this as a function of x. That means I'm going to need another equation from somewhere that involves h and x, so I can evaluate for, or solve for h, and plug it into this equation. So that's my goal, is to get this function in a single variable so I can find the derivative, set it equal to 0, find a max or a min. So what else did they tell us? They told us that it was a 4-liter container, and a liter is 1,000 cubic centimeters. So that means that the volume, which would be x times h, is fixed at 4,000 cubic centimeters. So there's my second equation. If I can solve this for h, I could also have solved it for x and written my area in terms of h, but I think you can see that'll be more difficult. So I have 4,000 over x squared. So now what I want to do is I want to take that and replace the h in my area function. And so now it'll be in terms of a single variable. So I have x squared plus 4x, so that's going to be 16,000 over x. So the 4x times that, so what I did was I multiplied the 4x times that. One of the x's cancels in the denominator. All right, so now I have my area function. So let's find the derivative. That'll be 2x minus 16,000 over x squared. And then we'll set that equal to 0. And if I move that over to the fraction to the other side, I'm going to wind up, when I simplify, I'm going to get 8,000 is equal to x cubed. So that means x is going to equal 20. All right, so now what we need to do is verify, is this indeed a maximum? Now, I can find the second derivative if you like. I'm just going to do a sign chart on this one. And I have x, I have a prime. When x equals 20, a prime is equal to 0. So let's pick a number smaller than 20, like 10. And where's my arrow? Here it is. So I want to plug 10 into this. So I'm going to get 20 minus, so let's see, that's going to be 16,000 over 100. So that's 160. So 20 minus, yeah, so we're going to get a negative value for a prime. So it's going to be a negative. And then if I pick a number bigger, like let's say 40, 40 squared is 1600, so that's going to be 10, and that's going to be 80, 80 minus 10. So that's going to be a positive value there. And so that tells me that my function a is decreasing, levels off, and then is increasing. So here I have a local minimum. So I verified that it's a minimum, and that's the only 0. So find the most economical shape. So now for my answer, I'm going to have a 20 centimeter by 20 centimeter by, and then the height, I'm going to need to calculate the height, so I'll go over to my equation here with h. And if I plug in 20, I'm going to get 20 squared is 400. 4,000 divided by 400 is 10. So h will be 10. So by 10 centimeters. And there it is. So I could do a bunch more of these, but the best way to do it is just to practice. So here are the key steps when you're solving these problems. First step, draw a diagram, label with variables and constants. Write a function for what you're trying to maximize or minimize. And by the way, that function needs to be in terms of a single variable. So sometimes if it's not, you'll need to write another equation, solve for one of the variables, and substitute it into the function. Then you want to find the derivative, set it equal to 0, and find local max and mins. Use the sign diagram or the second derivative to verify, and that's important. You can't skip that step. And then consider domain restrictions and check endpoints when necessary, like in the first example. So, here's the problems for you to try, and then we'll talk about them in class.